Now we look at what happens when we get the indeterminate form of type 0 times infinity. So if the limit of f is 0 and the limit of g is infinity or negative infinity as x approaches a, first of all, just from a direct substitution kind of perspective, we don't really know what 0 times infinity might turn out to be. Sometimes it might turn out to be 0, sometimes it might turn out to be infinite, sometimes it might actually turn out to be a non-zero finite number. So the way that we sort of deal with this situation is by rewriting this product f times g. So notice we're trying to now find the limit of this product f times g, and if we get that 0 times infinity form, what we can do is convert the product into a quotient so that we wind up with something that we can use L'Hopital's rule on. So for example, this f times g, just remember f divided by 1 over g, so dividing by the fraction 1 over g is the same as multiplying by its reciprocal g over 1. So that's the way they're converting from a product into a quotient. So instead of looking at the product f times g, we can look at the quotient f over 1 over g, and that would be equivalent. And similarly, we could instead look at it as g over 1 over f. That's equal to f times g. So then, once we convert the product to a quotient, we might have that same indeterminate form of 0 over 0 or infinity over infinity, so that we can use L'Hopital's rule. So it does ask you here to read example 6, and I strongly encourage you to do that. We're going to look at number 29 from your exercises in section 4.5. So as per usual, our first thing that we try is direct substitution. So this is the cotan of 2 times 0 times the sine of 6 times 0. And I don't know what you remember of cotan. That's 1 over tangent. That's the reciprocal function. And the tangent of 0 is 0. So 1 over 0 would give us that infinite situation. And then the sine of 0 is 0. So here we have infinity times 0. So our next step is to convert this product to a quotient. And so for that, again, as I mentioned just a second ago, the cotangent of 2x is equivalent to 1 over the tangent of 2x. That's just the definition of what cotan is. So that this limit, as x approaches 0, of the cotan of 2x times the sine of 6x can be rewritten as the limit as x approaches 0 of 1 over the tan of 2x, that's what the cotan 2x is equal to, times the sine of 6x. And so that we can actually write as a single fraction, so really we're finding the limit as x approaches 0 of sine 6x over tan 2x. And so if we do direct substitution on that, we're really finding the sine of 0 over the tan of 0. Of course, 6 times 0 is 0, and 2 times 0 is 0. And that's actually what gives us our indeterminate form that lets us use L'Hopital's rule. So once we know that, then we can say, okay, the limit as x approaches 0 of sine 6x over tan 2x, using L'Hopital's rule, I can take instead the limit as x approaches 0 of derivative over derivative. So the derivative of the sine of 6x is 6 times the cosine of 6x, using the chain rule. And the derivative of tan 2x is 2 times the secant squared of 2x, again using the quotient rule. And now I can try direct substitution on that. So I have 6 times the cosine of 0, again 6 times 0 is 0, and 2 times the secant squared of 0, 2 times 0 is 0, and the cosine of 0 is 1, so I get 6 times 1 in the numerator. And the secant, remember, is 1 divided by cosine. So 2 times the secant squared of 0 is 2 times 1, or 2. And so, in fact, the limit turns out to be 3, which is, sort of interesting. And again, I would encourage you to do a technology check on this. I don't have a ton of space to write on, so I won't. But if you're doing the technology check, I would use the original limit. Okay, so in other words, just to make sure that maybe you made some mistakes in your conversions, what you want to do is go back to the original limit of cotan 2x times sine of 6x, put that function in your y equals, and again, for cotan 2x, you don't have a cotan key on your calculator that I know of, depends on your calculator, I guess, but you can type in 1 over the tan of 2x, and let x approach 0 from the left and the right in the table, and see what the y values are approaching, and make sure that they are approaching 3. All right, and then last but not least, we have indeterminate differences. So here's where we might get the form infinity minus infinity. So if the limits of f and g are both infinite as x approaches a, then the limit of this difference can be converted. Again, our modus operandi is to try to convert that difference into a quotient. So in the previous example, we converted a product into a quotient. Here we're going to try to turn the difference into a quotient so that we might get one of the indeterminate forms that allows us to use L'Hopital's rule of either 0 over 0 or infinity over infinity. And again, I ask you here to read example 7. Please don't skip it. Actually read it and let me know if you have questions. Okay, so here is number 33. And notice we have a difference of 2 fractions here. Still, our first thing to try is direct substitution. So we'd have 1 over 1 minus 1 over ln 1. And that gives us 1 over 0 minus 1 over 0, or infinity minus infinity. So our next step to try to get this into a single quotient is to get a common denominator. Hopefully your algebra skills are good. So we can convert x over x minus 1 over ln x into a single fraction with a common denominator of ln x times x minus 1. So for example, my first fraction, I'm going to multiply top and bottom by ln x. And in my second fraction, I'm going to multiply top and bottom by x minus 1, so that I'm getting a common denominator of x minus 1 times ln x. Now, that's all I'm going to show for that piece of it, and we'll finish that in the actual limit. So the limit as x approaches 1 of x over x minus 1 over ln x is the limit as x approaches 1, and here is where I'm going to use my common denominator. That common denominator is x minus 1 times ln x. You could put an extra parentheses if you want. So what do I have? I have x times ln x from the first fraction minus 1 times x minus 1 from the second fraction. So in fact I have the limit. I can do a little simplifying here as x approaches 1 of x times ln x minus x plus 1 over x minus 1 times ln x. So using direct substitution on that, I have 1 times the natural log of 1 minus 1 plus 1 over 1 minus 1 times ln 1. So in the numerator, again, the natural log of 1 is 0. So I have 0 minus 1 plus 1. That gives me 0. In the denominator, I have 0 times 0, which is 0. So I do, in fact, get the indeterminate form of 0 over 0, which means I can use L'Hopital's rule. So now I'm going to take the limit as x approaches 1. I'm going to rewrite the original limit that I had, but then I'm going to say that's equivalent to the limit with the common denominator, the limit as x approaches 1, of x ln x minus x plus 1 over x minus 1 times ln x. So that's just rewriting the original limit in this quotient form. And now I'm invoking L'Hopital's rule. I'm taking the limit as x approaches 0 of the derivative, and I'm just going to put a line here to make sure that I don't get mixed in with other stuff. So how do I take the derivative of the numerator here? Well, in the first case, I have a product of x times ln x. So that derivative is the first times the derivative of the second plus the second times the derivative of the first, and the derivative of x is 1, minus the derivative of x plus the derivative of 1, which is 0. In the denominator, I also need the product rule. So that derivative is the first times the derivative of the second plus the second times the derivative of the first, and the derivative of x minus 1 is just 1. So now I'm going to do a little bit of simplifying. I'm taking the limit as x approaches 1. X times 1 over x is 1, plus ln x minus 1 over x minus 1 times 1 over x plus ln x. I don't really have to write times 1 on that. And the two ones in the numerator go away. So now I'm ready to try direct substitution. And I've got the ln of 1 over 1 minus 1 times 1 over 1 plus ln 1. That is, the natural log of 1 is 0. And in the denominator, I have 0 times 1, which is 0, plus the ln of 1, which is 0. Oh my gosh, look at this. I can use L'Hopital's rule again. I've got the indeterminate form a second time. So now I'm going to take, I'm running out of space here, I'm going to go back to the last piece I had, and I'm going to take the limit as x approaches 1, and now I'm taking derivative on the top and the bottom. Let me just delineate this out. I think I need to move over. Sorry about this. I ran out of space here. I'm taking the limit as x approaches 1 of the derivative of the top, that's 1 over x, over the derivative of the bottom. That requires the product rule in the first, times derivative of the second, plus the second times the derivative of the first, which is 1, plus the derivative of ln x, which is 1 over x. And now I'm going to substitute. I've got 1 over 1 in the numerator, that's just 1. In the denominator, I have 1 minus 1 times negative 1 over 1 squared, plus 1 over 1, plus 1 over 1. That gives me 1 over 0 plus 1 plus 1, which gives me 1/2. Wow, so in the end, after using L'Hopital's rule twice in a row, the limit of that original x over x minus 1 minus 1 over ln x as x approaches 1 turns out to be 1/2. And again, feel free to check that with technology using either a calculator in the tables or creating a table in Mathematica.